Welcome to our YouTube channel. This is Ernest coming to you from MathLab Tutorials in Toronto, Canada. Although seemingly impossible, like many other contributors on YouTube, our mission is to transform some of that destructive hate energy into constructive love energy for a subject that is so deserving. Mathematics is part of all that surrounds us. Just pause for a moment and take a good look. As your screen suggests, like it or not, math really did take us from the Stone Age to the Space Age. The sermon is over, and now let's get down to some serious math. This is video 5 of the video series on radicals, and I will show you how to convert radical expressions to expressions with rational exponents and vice versa. First we go through a note, and there are two ways to go here. We can take a radical and convert it to exponents, rational exponents, or we can take exponents and convert to radicals. Notice I indicated that radicals to exponents is a good idea, and exponents to radicals is not such a good idea. It's a bad idea. In calculus, when we encounter radicals, one of the first things we do is to convert them to fractional exponents or rational exponents. We very, very rarely go the other way around. We don't convert expressions containing rational exponents into radicals. Radicals are very difficult to deal with, whereas rational exponents are very easy to deal with. It's much more difficult to do algebra with radical terms than to do algebra with terms that contain exponents. It's very easy to apply exponent laws. It's more difficult to apply laws of radicals. Okay, that's why I indicate that going from radicals to exponents is usually a good idea, and going backwards is not such a great idea. Okay, I really think it's a bad idea, but you know, some teachers want you to go from exponents to radicals, so I'm including it in this video, but most of the time we'll be going from radicals to exponents, okay? Especially when you're dealing with higher level mathematics such as calculus, going from radicals to exponents is the way to go and not backwards. Anyway, that little bit of a sermon is over. Keep that in mind. We'll look at point number 1. We're going to be converting radicals to exponents, and as I indicated, that's always a good idea. And this is how we convert. The cth root of a to the power b converts to a to the power b over c. Notice that the c over here becomes the denominator of the b. That's essentially all that happens. So when you have a power like a to the power b and you have the cth root, it just becomes a to the power b over c. That's very easy to do. You just have to remember that the index of the radical becomes the denominator in the exponent, and b over c is called a rational exponent. So I call this the general conversion formula. And then there are some conditions. C is a member of the set 2, 3, 4. So in other words, the C value or the value of the index can be 2, 3, 4, etc. And the b, which is the exponent inside the radical, can be any integer. In other words, ... -2, -1, 0, 1, 2, etc. Okay, but the c value, the index of the radical, should be any integer greater than or equal to 2. Okay, now why does it work? If we let x be equal to the cth root of a to the power b, that's equivalent to x to the power c equals a to the power b. Okay, that's by definition of the cth root. Okay, so now we have x to the power c equals a to the power b. If we surround this equation over here with brackets and we raise both sides to the power 1 over c, which we can always do, then on the left we get x to the power c dot 1 over c. Well, you know that c dot 1 over c is just 1, so we get x. On the right hand side, b dot 1 over c becomes a to the power b over c. Okay, so we see that when x is equal to the cth root of a to the power b, it's equivalent to x equals a to the power b over c. Okay, now special cases. The cth root of a, the b value over here is really just 1, so the cth root of a is just a to the power 1 over c. Now, when the index does not appear on the outside of the radical, by default the index is equal to 2. So square roots usually do not have an index on the outside, but the index is understood to be 2. So this becomes a to the power b divided by 2, because there's really a 2 out here. So you get a to the power b divided by 2, and there it is, a to the power b over 2. And then, of course, the square root of a, there's a 2 that's understood on the outside of the radical, and the b over here, so the c value is 2, the b value is 1, and so a to the power b over c becomes a to the power 1 over 2. Okay? So let's look at an example here. The cube root of bracket 2x squared dot y dot z cubed to the power 4 easily converts to, all you do is copy paste this inside the brackets, and then the exponent becomes 4 divided by 3. That's 4 divided by 3. So altogether you get bracket 2x squared dot y dot z cubed is just copy paste from here. And the fractional exponent, or the rational exponent, by the way, rational and fractional mean the same thing. The rational exponent becomes 4 over 3, and we are done. Of course, we could continue to simplify this if we wanted to using exponent laws, but that's not the point right now. Okay, let's go on to the next slide. And point number 2, we're going to be going from exponents to radicals. And I indicated beforehand that this is a bad idea. It's not a great idea. But, you know, in a typical school setting, they'll do it in school. So here I go. Okay, I'm going to do it just to show you. That doesn't necessarily mean I think it's a good idea. In fact, I mean it's not a great idea at all. Okay, but I'm going to go ahead and do it anyway. A to the power b over c is equal to the cth root of a to the power b. That's the general formula. Of course, that's just the other one that I gave you just a few minutes ago, written backwards. Okay, it's just written backwards. Why it works? On the left-hand side, if we let x be a to the power b over c, okay, that implies that x to the power c equals a to the power b all to the power 1 over c. Okay, if you work this out, you get a to the power c dot 1 over c, which is x to the power 1. There it is. And of course, a to the power b dot, a to the power b dot 1 over c is a to the power b over c. There it is. Okay, that in turn implies, okay, if this to the power 1 over c is equal to this, it must mean that the inside must be equal. So we have x to the power c equals a to the power b. And of course, to solve this equation, we really need to take the cth root of both sides. So you get x to the power cth root of a to the power b. So all in all, we've shown that if x is equal to a to the power b over c, then x is also equal to the cth root of a to the power b. So in other words, these two expressions are completely equivalent. Okay, so special cases, whenever you see a to the power 1 over c, that really means the cth root of a. Whenever you see a to the power b over 2, that means the square root of a to the power b. And whenever you see a to the power 1/2, it means the square root of a. Okay, so let's go through an example. If we have bracket 2x squared dot y dot z to the power 3 all to the power 4 over 3, that's the rational exponent. Okay, you open up a big radical, you put the 3 on the outside, and you put the balance on the inside. So you put the 3 on the outside. The balance is just 2x squared dot y dot z cubed to the power 4. That's what's left over, and we are done. Of course, the inside can be expanded if you want to, but that's not the point here, so we're not going to do it. So let's go on to the next slide. And we're now going to be practicing going from radicals to exponents, which is a good idea. And let's see how that would go. Let's look at Q4a. We have the square root of 100.b.c cubed. Okay, now the square root, converts as power of 1/2. And 100 can be written as 10 squared, perfect square. B, you have to leave it alone. And then we have a c cubed. Okay, now if you distribute the 1/2, you get 10 to the power 2 dot 1/2, which is 10. You get b to the power 1/2, and then you get c to the power 3 over 2, and you can leave it like this. Okay, this is much nicer to deal with than this, especially in calculus. Okay, so let's look at part B. Over here we have the square root of 4m over 9. Okay, that easily converts to 4m over 9 all to the power 1/2. And of course, I took the liberty to write 4 as 2 squared and 9 as 3 squared, because now I want to use exponent laws to simplify this a little bit. In the next line, we get 2 to the power 2 dot 1/2, which is just 2 to the power 1. And we get 3 to the power 2 dot 1/2, which is 3 on the bottom. And then we're left with m to the power 1/2. So that would be the final answer. Let's go on to the next slide. Part C, we have square root minus 32h cubed all over m squared. Again, this one over here, we have to be a little bit careful over here. We know that m squared is always positive, no problem. 32 is positive, no problem. But we do have a negative here, and we have an h cubed here. In order for this square root over here to make sense, the argument has to be positive. That can only mean that minus h cubed is positive, and of course that in turn can only mean that h has to be negative. Okay, so h has to be negative. Otherwise, the square root of this quantity will be an imaginary number, and we're not looking at those things yet. Okay, that'll be in future videos. Anyway, the first thing I do is get rid of the radical. The argument over here goes inside the brackets, and the square root becomes power of 1/2. No problem there. Then I notice that 32 can be written nicely as 2 to the power 5. The minus sign I couple with the h, and I rewrite minus h cubed as minus h all cubed, and then the bottom is just transferred over. And now I can use the exponent laws over here. I get 2 to the power 5 dot 1/2, which is 2 to the power 5 over 2, no problem. I get minus h to the power 3 dot 1/2, which is minus h to the power 3 over 2. And then on the bottom, I get m to the power 2 dot 1/2, which is just m. And so this would be the final answer. Okay, now the assumption here, because we're taking square roots, is that we're assuming that m is positive and h is negative. Assuming that m is positive and h is negative. Okay, be very careful with that. Anyway, on to the next slide. Let's look at question 5. What we are doing is writing as mixed radicals. So they're going to give you some sort of an entire radical here, and our job is to reduce the radical to rewrite it in mixed radical form. Okay, we did this in the previous video, So let's go ahead and do it again. So we have the cube root of x to the power 3 dot y to the power 7. That's an entire radical. The idea over here is to rewrite as much as we can of the argument in terms of a perfect cube. Now the cube, so what I do over here, open up an empty bin, raise to the power 3. And I know that the cube root of x to the power 3 is x, so I drop in an x. And y to the power 7 decomposes as y to the power 6 dot y. And the cube root of y to the power 6 is just y squared, so I drop it inside the bin. And now, essentially, I'm going to expand this to figure out what the bad guy is. Recall that this is the good guy, x dot y squared, and I'm going to try to figure out what the bad guy is. Now, over here we have x to the power 3. We need x to the power 3, so we're done. Over here we have x to the power 2 dot 3, which is y to the, or y to the power 2 dot 3, which is y to the power 6. But I need y to the power 7, so I have a y left over. So the y is the bad guy. And the x dot y squared is the good guy. I'm going to extract this perfect cube from inside the radical. And of course, all you do is copy paste the inside of the brackets. And now it appears on the outside. And what's left on the inside is just y. So we have x dot y squared dot cube root of y. Again, the good guy was x dot y squared, and the bad guy was y, and we are done. We had an entire radical here, and now we have a mixed radical here. So now we're going to be doing the same sort of thing, but using rational exponents. We have bracket 64 x to the power 3 dot y, and it's all to the power 1/3, which you know means cube root. So the whole idea over here is to rewrite 64 as 2 to the power 6. X cubed is good to go, and the y. And now we can use exponent laws right across. So no problem at all. And when we use exponent laws, we get 2 to the power 6 dot 1/3, which is 2 to the power 2. And over here we get x to the power 3 dot 1/3, which is just x. And then we have y to the power 1/3. Okay, now you know y to the power 1/3 means cube root. 2 squared is just 4, so we have 4x. And this is just the cube root of y, so we can just rewrite it like so. I'd prefer that you just leave it as 4 dot x dot y to the power 1/3, but they want you to convert to mixed radicals. So what am I supposed to do? There you go. But again, this is equivalent to 4 dot x to the power 4 dot x dot y to the power 1/3, and from a calculus standpoint is much preferred to 4 dot x dot cube root y. So there you go. Part C, the same sort of thing. We have bracket 16 x to the power 8 dot y cubed to the power 1/3. And so what I'm going to do is open up a cubed bin over here, empty bin, raised to the power 3. Okay, that's essentially what I'm going to do. I didn't have to do it like this, but I chose to do it like this. Now 16 can be decomposed as 8 dot 2, and I know the cube root of 8 is 2. There you go. And x to the power 8 can be decomposed as x to the power 6 dot x squared, and the cube root of x to the power 6 is x to the power 2. Drop it inside the bin. And the cube root of y to the power 3 is just y. Drop it inside the bin. And now we're looking for the balance. We know that 2 to the power 3 is 8. We need 16, so the balance is 2. And we have x to the power 2 dot 3, which is x to the power 6. We need x to the power 8, so the balance is x squared. And then we have y to the power 3. We need y to the power 3, so the y does not appear. And then we can use exponent laws over here to extract. Okay, we know that something cubed to the power 1/3. 3 dot 1/3 is 1. So we get 2x squared dot y, there it is. And then we're left with this, which is 2x squared to the power 1/3. Okay, then at the end we can convert this to cube roots because the power 1/3 means cube root. And so we have a 2x squared dot y on the outside, that's the good guy. And then we have cube root 2x squared, so 2x squared is the bad guy. And then we're done. Okay, let's go on to the next slide. More operations with radicals. So these will be like miscellaneous operations. I believe these are just joining up radicals together. So we'll look at 6a. We have the square root of 6m squared dot the square root of 2mn cubed. When you join up the radicals together, which we can always do because this is of the form root a dot root b, and we know that's equal to the root of a dot b. So all you do is join up these two terms together. We get a big square root. We get a 6.2, which is 12. M squared dot m is m cubed. And then we're left with an n cubed here. And now it's time to extract, and we're dealing with square roots. So I open up a big square root over here, open up an empty bin, raise to the power 2 as usual, and leave this blank. Now I look at the 12, I can decompose that as 4.3. The square root of 4 is 2. Drop it inside the bin. M cubed can be decomposed as m squared dot m. The square root of m squared is m. Drop it inside the bin. And n cubed can be decomposed as n squared dot n. And the square root of n squared is n. Drop it inside the bin. And then we're looking for the balance, which is essentially the bad guy. So we have 2 to the power 2, which is 4. We need 12, so we need 3 out here. We have m squared. We need m cubed. We have an m out here. And we have n squared. We need n cubed, so we have another n out here. So the good guy will be 2mn. The bad guy will be 3mn. Okay, so now we extract outside the radical. And all you do is copy paste the inside of the perfect square. And we get a 2mn out here. And we're left with the bad guy inside the square root. So we're left with 3.m.n. So we have the good guy on the outside, the bad guy on the inside, and the radical has been reduced. Let's look at b. We have minus 5 square root 10x dot y. Dot 3 square root 2x squared dot y. Okay, so the first thing I want to do is join up these radicals, but these radicals each have their own coefficients. So all I do is multiply minus 5.3 to get minus 15, and then join up the radicals together. Again, we're going to use the fact that root a dot root b is just root a dot b. And so 10.2 is 20, and x dot x squared is x to the power 3. And y dot y is just y squared. Okay, so we carry the minus 15. We put a big square root. We open up empty bins, or an empty bin, sorry, raise to the power 2, and leave this blank. 20 decomposes as 4.5, and the square root of 4 is 2. Drop it inside the bin. And then x cubed decomposes as x squared dot x. The square root of x squared is x. Drop it inside the bin. And of course, the square root of y squared is just y. Drop it inside the bin. And then we're looking for the balance, which will turn out to be the bad guy. The minus 15 has already been done, so you just carry it. So we get a 2 to the power 2, which is 4. We need 20. So we drop in a 5 over here. And we have x to the power 2, which is x squared. We need x to the power 3, so we drop in an x. And we have y to the power 2. We need y to the power 2. So nothing for the y. So we identify the bad guy as 5.x. The good guy is 2x.y. Now we extract. And we get minus 15.2.x.y. And we're left with the square root of 5.x, which is the bad guy. At the end, just simplify out here. We get minus 30.x.y, and then the square root of 5.x, and we are done. I think it's over and out for this video. I'll see you soon. Take care. Thanks to all for viewing this video. Stay tuned for many more videos to come. If you liked the video, please give us a like, submit comments, and subscribe to our channel. If not, please tell us how to improve it. Over and out from Ernest at MathLab Tutorials in Toronto.